the second derivative of a vector function. So just as for real valued functions, the second derivative of a vector function, you have a vector function r is the derivative r prime, that is r double prime is just equal to, well, the derivative of r prime, so we're going to have a double prime there. So basically we just take the derivative again and again, just repeat the same thing. So for instance, the second derivative of the function in example 3 is, and if we recall the derivative of example 3, that's this right here. So r prime of t is equal to negative 2 sine t cosine t and then 1. So we have, just recall, this is going to be equal to, this is of t, equal to negative, this is going to be sine, negative 2 sine t, and then this is going to be, cosine t, and then we'll just take it with, and then 1, like that. And I quickly teleported here, just double check. So negative 2 sine t, cosine t, and 1. Yeah, so that's what we have. And then the second derivative, well, we just take the derivative of the derivative. So this equals to r double prime of the vector function, and derivative of negative 2 sine t. The derivative of sine is just cosine, so we're just going to get 2 cosine t. Then this one here, derivative of cosine t, that's going to be negative sine t. And then derivative of 1 is just 0. So that's what we have. So we could just box this whole thing in. And now note that in a future video, we will see how the r prime of t and r double prime of t can be interpreted as the velocity and acceleration vectors of a particle moving through space with position vector r of t at time t. So stay tuned for those videos. And now go to the next section, so differentiation rules. The next theorem shows that the differentiation rules for real valued functions have their counterparts for vector valued functions. So here's a theorem. Suppose u and v are differentiable vector functions. C is a scalar and f is a real valued function. Then, and I'm going to list them all here, and I'll also show a screenshot of my calculus book just for more concise typing there. So we're going to go, the first property or a differentiation rule is just regular addition or subtraction. So d over dt is the derivative of the addition of two vector functions, u of t plus v of t. This just equals to, well, you could just separate these. So we could just take u prime plus v prime. So that's the first one, and I'll prove all these in exercises. And then theorem or property 4 or rule 4. I'll do that like right after this one. So number 2 is going to be, well, this is just going to be if you have d over tt, and if you have a constant. So if you have a c, u vector like this, t, and then the derivative of this is just gonna be the same thing as taking the c out and just taking the derivative of the u. So just take the constant, c is a scalar or a constant. Just get that out of there. So now the part 3, this is gonna be differentiation part 3, or property 3. So this is d over dt equals to, I know that now we have a function. So instead of just one, these ones are pretty much the same thing. This one's just a constant or scalar. This is the function like this, and then u of t. This equals 2, and then this one would just have to use product rule. So this will equal to f prime of t, u of t, like this, and then plus f of t, u prime of t. Okay, like that. So we have that. And now the next one is number 4. So number 4 is going to be d over dt, and this one is the dot product actually. So this is going to be, now if we have a u of t dot v of t, this equals to, this equals to, well, it's actually going to be very similar to this above one, just using product rule. This equals to u prime of t, and then dot v prime of, just v regular t, and then plus, now we do the reverse. So u vector dot product with the v vector prime of t. So it's kind of like the product rule, but with dot products. So fascinating stuff there. And now the next one is going to be this part 5. This one's going to be using the cross product. So d over dt, and it's going to be the same thing as the dot product one. And then that'll be cross v vector of t. This equals to, this is going to be u prime of t cross v normal. And then plus, and now we do the other side there. This is going to be u vector t cross v vector prime of t, like that. And now the last formula or rule is going to be number 6. This one involves the chain rule. So d over dt of, you have now u vector, instead of t, now we have a function is inside as a parameter instead of just a regular t. So that equals to, now then basically what this equals to is, well, using chain rule, well, we're going to have to, what ends up happening is take the derivative afterwards. So we're going to have this f prime of t gets out of there and then multiplied by, well, u prime of t. So the order would be you take the derivative u prime of t like this, and then take the derivative of the inside function f of t and take it out. So again, this is just chain rule. Chain rule. Put this in normal bracket. Yeah, just put that chain there and then rule like this. Like that. All right. All right. And going further, so we have these rules. And now here's a screenshot of the list from my calculus book just to make it more concise. So there it is. And also that was a way to double check there. So this is how it looks like. So yes, and basically there's those 6 there. And now this theorem can be proved either directly or by the definition of a vector function derivative, or from the theorem on differentiating vector functions by components. And I'll be doing that. I'll be using both to prove them in the exercises.